Writing the equation for a typical radioactive decay. So now the training wheels really are off, but we do actually have enough information to answer the question here. So for example, this type of nuclide notation is fairly common because we do not need to be given Z if we've been told what the element is. So you can look up mercury on the periodic table and we see that mercury has Z equals 80. So you should be able to just go ahead and write the symbol for a mercury nuclide from that information. We're told it decays via electron capture. So the symbol for an electron is going to be 0 and then -1 on the charge, no mass, and a -1 charge on the bottom. And we usually give that the symbol either a beta or an electron, that's fine. Okay, so it's going to be on the left-hand side of the reaction. So then what we need to work out is the daughter nuclide that is being produced, okay? So we have to sum A to find what goes on the top, and then sum Z to find out what goes on the bottom. Electron capture, the only other product is usually gamma radiation, but we'll deal with that in a second. So 201 plus 0 is still going to be 201. So that will be our mass number, and that is typical for electron capture reactions, that the mass number remains unchanged. 80 minus 1 is 79, so the proton number has decreased for 1. Again, that is typical for electron capture, that a proton is changed to an electron, essentially, right? We lose 1 in the proton number. So 79, we would have to look that up in our periodic table to see which element has Z of 89, and that is gold. So usually for these kind of reactions, the energy is released in the form of gamma ray. Gamma ray has no mass and no charge, so you're totally okay writing 0 and 0 here. And I'm going to just freestyle the symbol for gamma radiation as good as I can. So it's the Greek letter gamma. So usually electron capture, you would expect to see gamma radiation being emitted as well. Alpha and beta decay, there is gamma released later. We don't typically include it as part of the balanced reaction. Okay, so for this example, we have the beryllium-10 nuclide decaying by beta emission. So beta emission, beta is an electron, and emission means it's going to be on the right-hand side. So beryllium-10, we know the mass number is 10, we know the element identity is beryllium, and we can work out the proton number, the atomic number, by looking at beryllium on the periodic table, and that is 4. Okay, so beta emission means we're going to have an electron on the right-hand side. So an electron is 0 and then -1, and then usually E for an electron. Let's make that look a bit prettier. So the parent nuclide is beryllium-10. What is the daughter nuclide going to be? So the mass number 10 must be 0 plus what our mass number is for our daughter nuclide, which is also going to be 10. 4 has got to be equal to -1 plus something, so that'll be +5. So Z is changed. So Z of 5 is going to be boron. So let's just check. 10 plus 0 equals 10. Check. And 5 minus 1 is 4 equals 4 on the left-hand side, so check, okay? So that would be our balanced beta emission equation. All right, so one more just for fun then. So we have samarium-147 decaying by alpha emission. So first of all, let's write the symbol for samarium-147. Samarium is down there in the lanthanides. So that's Z of 62. Okay, alpha emission, so that means the alpha particle, which is the helium nucleus, helium-4 nucleus, is on the right-hand side. So 4, 2, helium. So let's work out what the daughter nuclide can be then. Okay, so 147 equals our mass number plus 4. So that means it has to be 143. How's my math today? 143 plus 4 equals 147. Check. Okay, and on the bottom, 2 plus something equals 62. So then my Z must be 60. So our identity of our nuclide has changed, right, by emitting an alpha particle because it's lost 2 protons in the nucleus. So Z of 60 is blah, 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 neodymium. So neodymium plus that alpha particle being emitted. So there we go, balance. 143 plus 4 is 147, 60 plus 2 is 62. And that's all there is to it.